Hi everyone, I am Shrutika Panda. I am again here with my new topic, aromaticity. This is my lecture number 2. So, in lecture number 2, I have chosen one organic chemistry topic. It is from general organic chemistry. So, it is basic to learn organic chemistry. So, it will be not only helpful for CSIR NET, it will be helpful for any kind of exam. Overall, to understand organic chemistry, you have to have this idea about this chapter. Okay. So my purpose is simple here. I want to reach you through my teaching. I want you I to make patience and practice with me, and so that you can have the courage and to crack the CSIR NET exam. Okay, so that I will help you. I want to introduce various new topics to you in a easy and interesting manner, and I want that it will be uh, I hope it will be helpful for you all. Okay, that is my only purpose and duty here. So let's start with a new chapter with a positive energy. Okay, let's start there. So first, I will introduce you how why this chapter is important and why this terminology actually came. Why that I will start with, and then I will go through go to the some important terminologies and important. I will introduce some important structures, and also then after a few slides, I will strictly go to some questions and practice session. Okay, so let's start and you all listen with a copy and a pen and paper. Okay, that will be helpful for you all. So let's start. So first, what is the difference between these two? One structure is here, right? Yeah, other one is. So tell me, what is the difference between these two? This is, we all know this. This is benzene, right? We are not now child. We all know this is benzene. And this is cyclooctatetraene, right? Okay, forget about it. Forget about the names. What is the difference between these two? What is the difference between these two? Tell me. So, one difference I can see from your eyes, that is, this has 1, 2, 3, 4, 5, 6, 6 carbon atoms with 3 pi bonds. This has 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon and 4 pi bonds. This is 6 carbon and 3 pi bonds. So what? Both are cyclic, having pi bonds, right? And all the atoms are carbon and hydrogen only. It has. So what is the difference? What can be the only difference in chemical, their chemical property? Let's see. When we are introducing Br2 here, substitution product is formed. And when we are introducing Br2 here, addition product is forming. Both these two products are actually different. So, how it is different? For substitution case, what is happening? One hydrogen is replaced by one Br. And here what is happening? In the addition product, addition in the addition case, sorry, for the addition case, what will happen? So this is happening like, yes. So for the addition product, what is happening? So here Br and Br will come and one double bond will go away. Okay. So why this? This is totally different product, right? So why this is happening? We know addition. Addition. What is addition? For alkenes, simple alkenes, double bonds. This is a common chemical property of a double bond or alkene, that it will give addition product. It has electron density. It will attack Br two. So like that way, two Br actually attaches the two ends of the double bond. That is a simple phenomena. So this is not odd, right? This is giving addition product. This is not odd. This is natural. But why here substitution product is here? Why? How? That is the question. So and only one pi atom extra is extra here. So how this is affecting? So scientists are actually performing various research to know the answer why it is happening. And another interesting thing is that heat of hydrogenation. So what is heat of hydrogenation? Heat of hydrogenation is when we add hydrogen to the system will form like reduction. It will form this, okay, and this for this case will form, okay. So this is simple reduction. So the if we see energy profile diagram, so this energy level for this benzene is less, and here let's say benzene energy level is this, and for this case it's energy. Okay. For this case, let's say the energy is here of this molecule, and after hydrogenation, actually the stability of the product increases, so it goes to like this. Okay. So it is seen that heat of hydrogenation. So it is the heat of hydrogenation, right? The difference between reactant and product, heat of hydrogenation, delta H1 and this delta H2. So it is actually seen that the heat of hydrogenation for benzene is is less. It is less than heat of hydrogenation of this cyclooctatetraene. But they are actually same kind of molecule having these double bonds. Okay, so why this kind of difference is there? Okay, so not only the it is greater, it is less. The point is that it is very similar to, if we consider ethylene molecule, 4 ethylene molecule, the heat of hydrogenation will be the similar like 4 ethylene molecule here. But here, if we take 3 ethylene molecule, it will be actually similar. What I am trying to say is, if we take 3 ethylene molecule, then the heat of hydrogenation value will be more for this 3 ethylene molecule and less will be for benzene. And if we take 4 ethylene molecule here, and the value of heat of hydrogenation will be similar to this molecule. So why it is different? Why it is so different than 3 alkene? It is simple. You can say this is ethylene, this is ethylene, this is ethylene, right? So it should be, but it is not. So the problem is not here, problem is here. It has something new property that we have to investigate. The scientists actually investigated this and we are reading it now. So let's talk about this aromaticity. Then this kind of word came into our chemistry. So what is now aromaticity? Scientists were actually puzzled to see such result, and the aromaticity is a explanation to this kind of problem. So what is aromaticity actually? A property of some organic molecule by which the molecules gain extra stability than expected. So it is it wants to say that benzene is extra stable if we join 3 ethylene molecule. Okay, ethylene molecule. The stability of these 3 ethylene molecule combined will be not will be less than benzene. So it has some extra stability. So it is aromatic. But only now the question is only benzene is aromatic? Only if we see this kind of six membered cyclic, this three pi bond is there, this kind of like benzene is only benzene is aromatic, or some type of here a property of some organic molecule. So how can we actually find out that which will be aromatic or not? Now we are coming to the Huckel rule. Huckel actually he was a scientist, so he has done some experiments, and he has found a conclusion, and Huckel's rule is there, which is very important to identify the aromatic compounds. So which organic compounds we can say is aromatic? Let's see the Huckel rule. Planar, fully conjugated, cyclic system with 4n plus 2 pi electrons are exceptionally stable. Such systems are called aromatic. So not only benzene, we have other companion too. So planar, three things are there. Planar, fully conjugated, cyclic systems with 4n plus 2 number of pi electrons. Okay. They have a closed cell of why it is extra, it gains extra stability. So to it will come to their it will come from their energy molecular orbital diagram. So in this diagram actually they have a closed cell of electrons in all bonding orbitals. So they are explaining that it is the reason for their extra stability. Let's not talk about this much. Coming to this benzene. So it is so let's talk about these conditions. It is planar, obviously. sp2 carbons are there. Planar, fully conjugated. Yes, of course. Okay, let's see this. This will be can goes to this. This can go to this. This. So fully conjugated, right? Cyclic, obviously, with 4n plus 2 pi electrons. How? Pi bonds are 3. So pi electrons will be 3 into 2 is 6. So 6 can be written as 4 into 1 plus 2. Right? So 4 here n equal to 1. So here n can be 0, 1, 2, 3, 4, 5, 6, etc. Okay. So n is 1 here for the case of benzene. So we can prove that benzene is aromatic for this with this rule. Now coming to aromatic compounds and their properties. Planar, we have previously read it, right? Planar, cyclic, conjugated, and follow Huckel's rule. Here comes the main thing. Huckel's rule means 4n plus 2 number of pi electron it should have. Okay. Benzene we have seen. Okay, this one. So here pi electrons are only we are counting, right? 2 pi electrons, 2 pi bonds are there. So 4 pi. Is it 4 pi? No. Because if in a cyclic system, this negative charge is here, in this negative charge will be in p orbital. And we know pi bonds are actually, this is p orbitals, right? All are p orbitals. Okay. So overlap between p orbitals actually result the pi bonds. So it is also in p orbital. So it can goes to this, it can goes to this, it can go to this. Okay. So conjugation is here, and it is not only a lone pair, it will be counted in the pi electrons. Okay. So this is the case. So now we have to calculate 2, 2, 2, 6, 5. Again, 4n plus 2, 4 into 1 plus 2 equal to 6. N equal to 1 here. Again, aromatic. Now this one. Okay, let's just, okay. Okay, this one. Here positive charge is there only. So it has a vacant. Okay. So number of pi electrons, 2, right? But 2, how can we get, we can say this follow or not. Let's try 4 into, let's say 0 plus 2. What will it give? 2, right? So here n equal to 0. So this is also aromatic. So these 3 are aromatic. Okay. Like this way, if you have given some structures with various pi electrons, so first you have to see, is it planar, is it cyclic, is it conjugated or not, and then you have to count 4n plus 2 pi electrons it has or not. Okay. So all the 4 criteria will be fulfilled for aromatic compounds. All are planar, sp2 carbons, sp2 carbons. Okay. So all are planar, cyclic, conjugated, and follow Huckel rule. 4 criteria you have to remember. Okay. Next, one another kind of molecules are there which are anti-aromatic. How can we find that? Planarity is same like aromatic, cyclic, obviously, complete conjugation like aromatic, but doesn't follow Huckel rule. How? It will not follow 4n plus 2 number of pi electrons. It will follow 4n pi electron rule. 4n number of pi electron will be there. Okay, let's take an example and understand. So this one is aromatic, right? Count 2, 2, 2. Oh, yeah, we have actually done this. Okay, let's come to this. This is aromatic. Arrow. Okay, 6, 5. Okay, here 1, 2, 3, 4, 5, 6. But oxygen has lone pair, right? We have to consider that also because it goes to conjugation, right? It will goes to this, it goes to this, it goes like this, it goes like this. Yes, it goes like this, negative charge. Okay, so it is conjugated obviously, and pi electrons of these lone pairs will be counted. The lone pair electron will be counted in number of pi electrons. Okay, so the number of pi electrons here, what will be the number of pi electrons? 1, 2, 3, 4, 5, 6, 7, 8. 8 pi, right? So is it following 4n plus 2 or 4n? Let's try this. 4 into 2 will be 8. Here n equal to 2. So it is anti-aromatic compound. Anti-aromatic. Let's say if we take, instead of negative charge, if we take, okay, let's clear this. Instead of this negative charge, let's say we took positive. Okay, now number of pi electrons 1, 2, 3, 4. 4 pi, right? 4 pi means 4 into 1 pi. Okay, so it follows 4n number of pi electrons and it is fully conjugated, planar, cyclic. Okay, so it is also anti, it is now becoming anti-aromatic. I hope you understood, and we will again solve some questions and practice some structures. So then you should not have any doubt after that. Now coming to a comparison. But here, if you see, again another a new term is here, non-aromatic. Okay, let's not talk about this. Let's see what I have written here. Aromatic, anti-aromatic. Planar, sp2 or sp atoms are there, planar. Cyclic, cyclic. Fully conjugated, fully conjugated. Follows Huckel rule, 4n plus 2 number of pi electrons. Doesn't follow Huckel rule, it follows 4n pi electrons. Right? These actually we have read till now. Okay, there is no doubt about that. But why it is vacant? Because the only if you remember only one line here, you will understand which will be non-aromatic. Here 4 conditions are there, right? 1, 2, 3, 4. If any of the 4 conditions are not fulfilled by any of the structure, then that kind of structure will be called non-aromatic. If any of the conditions, here conditions are 1, 2, 3, 4. If any of the conditions are not fulfilled, okay, understood? Okay, let's take an example. Examples are here. Okay, so it has how many number of pi electrons? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. 8 pi electrons. So it should be anti-aromatic, right? Should be anti-aromatic, right? I have also shown you one example here. No, this is different, right? Here oxygen molecule is here and it is 7-member ring. Okay, so here 8 pi electrons. There also 8 pi electrons are there. So you will say yes, like this 8 pi electron and 4 in number of pi electrons they are following, so it will be anti-aromatic, right? But here it is not, because it will not be planar, it will be tub shaped. These are double bonds here also, so this will be tub shaped, it is not planar. So one condition is not fulfilled here. If any of the conditions are not fulfilled, this will be non-aromatic. So this compound will be non-aromatic. Here also same thing happens. It will not be planar, and here is also same thing happens. I will talk about this in later slides also. Let's for now only just look at the examples. Okay. Now it is stability order. It will be very helpful. Sorry. In later slides. Okay, let's first come to homoaromatic compounds. Okay, what is homoaromatic? We have till now we know actually aromatic, anti-aromatic, then non-aromatic. Now homoaromatic. Let's not be confused about the regarding the terms. Okay, just see only the structures and the conditions. Just only remember this. So what is homoaromatic? Stabilized cyclic conjugated system is formed by passing one saturated atom. Saturated? Why saturated is written here? Let's see. This is an example. So cyclic and conjugated system between sp2 atoms. Okay, it is conjugated obviously. This can goes to this conjugated, but this is sp3, so it is not fully conjugated. It is conjugated only between these sp2 carbons, but here sp3 carbons are also present, right? So conjugation will be interacted. Okay, here is also another example. So 1, 2, 3, 4, 5, 6, 6 pi electrons. Okay, you will say it will be aromatic, 6 pi electrons. No. Why? It is not fully conjugated. Here not positive, negative, anything is not there. So it is sp3 carbon. How it can participate in conjugation? It will not, right? So stabilized cyclic conjugated system passing by a sp3, one saturated atom, not unsaturated. So it will not be a part of conjugation. So what will happen here? The scientists are actually saying that it will be stabilized like this way only. So sp3 carbon goes to out of plane, means upside. So it will, this is sp3, and the other part remains in planar form. Okay. So they are saying that some actually proofs are there that a little bit of partial conjugation is happening here, as it is sp3 carbon is not in the plane, it is upside. So partial conjugation is there. That's how it can be a little stable, not like aromatic systems. It is a little bit of it became little bit of stabilized. It gained little bit stability. Okay, understood. Here is also same thing will happen, but how can okay, this is positive. Oh, this is to now this. Oh, okay, like this. It will be out of plane. This is a switch. Okay, like that way we can see. We can show now. Okay, let's come to the stability order. Stability order of all the compounds we have read till now. Type of compounds we have read: aromatic, Huckel rule will be followed, cyclic, planar, conjugated, right? Homoaromatic, right now we have studied, right? It will be actually conjugated through in the sp2 parts, but one sp3 carbon will be present, so full conjugation will be not there. Conjugation will be interrupted by sp3 atom. Okay. Non-aromatic, any four condition of the aromatic and anti-aromatic, when it is not fulfilled, any of the four conditions, then it will be called non-aromatic. And anti-aromatic, yes, 4 and 5. So what will be the stability? So it is actually, it can be seen that aromatic compounds are most stabilized. Okay. That's how we actually started this class, right? Why benzene is so much aromatic, right? So aromatic compounds which are following Huckel rule, planar and cyclic, fully conjugated, these are actually most stable. Then comes homoaromatic. Okay. Then non-aromatic, then anti-aromatic. It is actually seen that the anti-aromatic compounds are highly unstable compounds. This is a property of anti-aromatic. These are highly unstable. Okay. So one thing is clear: aromatic will be more stable and anti-aromatic will be least stable. Okay. And in between these two, how can we actually recognize? So in the case of non-aromatic, in the case of homoaromatic, we have seen that one sp3 atom actually became non-planar, and other sp2 actually they are in plane, and partial conjugation is there. So from that we can say that it gains some little bit of stability, right? And in the case of non-aromatic actually it is more stable than anti, but less stable than homo. Okay, please remember it because it will be needed for question. Okay, so we have done this. Now practice time. Let's take your pen and paper and start with me. Okay, so first this compound. Okay, first one is this propylium cation. Okay, so it has one pi bond, and right, and it is positively charged, so no electron, so only 2 pi. Okay, so the four conditions were cyclic, planar, conjugated, and 4 is 4n plus 2. Okay, it is the criteria for aromatic, and for anti-aromatic it will be 4n. Okay, so let's just practice a little bit, so you will understand it yourself. Okay, so 2 pi electron, it will be, it is planar, obviously cyclic, conjugated, 2 pi electrons is there, so 4 into 0 plus 2, n equal to 0. Okay, so it is aromatic, obviously. So for aromatic we are writing A only. Okay, here second example, 1 2 3 4. So it is cyclic, it is planar, it is conjugated, and having 4 pi electrons. Okay, so 4 into 1 pi electron, n equal to 1. It is anti-aromatic, 4n number of pi electrons is here, right? So anti-aromatic, AA we are writing this aromatic. Okay, now coming to this third one, 2 positive charges are here, but here we are not, yes, so conjugated, number of pi electrons 2 pi, 2 pi, obviously 4 into 0 plus 2, so it will be aromatic. It has 2 plus 2, okay, means 4 pi, anti-aromatic. Then nitrogen has a lone pair, but it is not participating in conjugation. If you see, it is already a sp2 atom, and it has a double bond here. So it can be conjugated, it cannot conjugate further through this lone pair, right? It has conjugation, but in this way, in this way. This is not participating, right? You are getting or not? If there is not any double bond here, then it will participate. It will conjugate through this double bond. It will goes to here and here. But here, this lone pair is not participating in the ring conjugation. Here already 2 double bonds are here. So 4 pi only, not 6 pi. It is 4 pi. So 4 pi again anti-aromatic. Anti-aromatic. Here 1, 2, 3, 4, 5, 6. 6 pi. Obviously planar. It will be planar, right? 4 carbons are there. So planar, conjugated, and all are sp2. So it will be planar, obviously conjugated, and 4n plus 2 number of pi electron it has. Right? Right? 6 pi aromatic. 1, 2, 3, 4. 4 pi. Planar, conjugated, and having 4 pi electron. 4n rule is followed. Anti-aromatic. Okay, here 1 2 3 4 5 6, 6 pi. We have actually taken that this example before, so it will be aromatic, right? Here what will be the this compound? See, 4 pi electron. Okay, it is planar. Is it planar? Well, let's not talk about this. Conjugated, between the sp2 it is conjugated, but here one sp3 atom actually present. Sp3 atom, right? So in which criteria or in which of the characteristics, it is the characteristics of homoaromatic compound, right? Not fully conjugated, conjugation is disrupted by one sp3 atom, so it will be homo. Let's not then see the about the number of pi electrons, it is planar, not nothing. Only you can, if you see the sp3 here, it will be homo, right? No, no, sorry. Sorry, my mistake. For the HOMO, it was there like it will be actually non-aromatic. It is not fully and conjugated. It will be non-aromatic because for the HOMO, the condition is sp3 carbon is there. The condition is there, but what will happen is that in the non-aromatic compound, we have told you that any of the conditions, if not fulfilled, then it will be non-conjugated, right? Non-aromatic. So here it is not conjugated, so it is non. Because in the case of homoaromatic compound, it gains some extra stability by the conjugation of the planar part. So here the planar part has 4 pi electrons. It will not give any extra stability to the molecule, right? 4 pi means anti-aromatic criteria. So it will be non-aromatic. Okay. Only consider homoaromatic if the sp3 carbon is there and also the rest part is aromatic, behaving like aromatic. Okay. So it will be non-aromatic. So I have also done some mistake like you guys, right? So please remember this. It will be non-aromatic. So here boron is here. So we have seen that heteroatom can present and nitrogen, oxygen. We have seen this. It can donate their lone pair and be a part of the conjugation. But boron has no donatable lone pair, right? 3 electrons it has and it actually forms 3 sigma bonds. So now then how we can consider it? It is seen that actually it behaves like C plus. C plus means cationic carbon. As it is in the periodic table, it is the left actually boron, after boron carbon comes na, in a period, right? So boron carbon, nitrogen, oxygen, fluorine, like that way. So boron has 1 carbon less than carbon, right? Boron has 1 carbon less than carbon. So it will behave like carbon plus, cation. So if we consider cation here, then it can be conjugated, right? But it has 4 pi electron. 4 pi means anti-aromatic, right? So it will be anti-aromatic. So what we should remember here? Boron acts as carbon positive and it will be conjugated, and then count the pi bonds. So here 4 pi electrons are there. Boron has no lone pair, so 4 pi electron, it will be anti-aromatic. Simple. Here again, pyridine. Nitrogen is here. Nitrogen has lone pair. So how you will count the pi electrons? 6 pi or 8 pi? Will be 6 pi, right? Again, I am telling you, if the yes, so if the lone pair is not involved in the uh, conjugation, then we are not we not will not count that lone pair in the 4n plus 2 or 4n in the Huckel rule, actually counting the pi electrons. So here 6 pi electrons are present. It is aromatic, obviously. Other criteria are also fulfilled. So here the same thing. All are conjugated double bonds. So lone pair is not participating. Lone pair is not participating. So 6 pi aromatic. Here you can see lone pair. What about the lone pair? You told me. Here no double bond is there. So it can goes to here, it can go to here, 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 right? Conjugation is there, fully conjugated system. So it will be fully conjugated system. Now count the pi electrons. 1, 2, 3, 4, 5, 6, 6 pi. Aromatic. Yes. Then this same thing. But here 2 lone pairs are there. So will you count 2 lone pairs? Will you count 2 lone pairs here? we know that two p orbitals are perpendicular to each other. Okay, so if it is px, this is py, so perpendicular to each other. So the conjugation will happen when parallel p orbitals are present. If you consider the other p orbital like this way, so the lone pair in this p orbital, it will be only conjugated to the whole system. But the lone pair here, it is in 90-degree angle with rest of the p lobes, p orbitals. So it will not participate in the conjugation. So we'll count. Although it has two lone pairs, oxygen has two lone pairs, one lone pair can participate in the conjugation, other will be outside, other will not be a part of conjugation. So here 6 pi, right? Sulfur, same thing, two lone pairs are there, but it is not participating in conjugation, so 6 pi aromatic. Okay, so till now you are clear, right? Now coming to the more complex structures. Here 1, 2, 3, 3 pi, so 6 pi, all are conjugated, sp2, planar, all the criteria are fulfilled, aromatic. Here we are considering it as a C plus, so it will be aromatic like this. Here 1, 2, only one lone pair will be participated, so 1, 2, 3, 4, 5, 6, 7, 8, 8 pi. So it is following 4 into 2, 4 in number of pi electrons, is equal to 2 here, right? It will be anti-aromatic. Okay, here 1, 2, 3, 4, 5, 6, 7, 8, 8 pi, again anti-aromatic. Okay, here 1, 2, 3, 4, 5, 6, 7, 8, 8 pi, right? Same anti-aromatic. Anti-aromatic is it? You will never know if it is anti-aromatic or not, because you have to have the idea about structure. So in the at the starting of the video, I have told you that some part is there, some parts are there which you have to remember. So that's why I have put this much of examples here, so that you have the clear knowledge about all the structures. So here when heteroatoms are present, this will be anti-aromatic because 8 pi electrons, but here 8 pi electrons are there, but here only lone pair present instead of this heteroatom. Here in this case what will happen, it will goes like tub shaped form will be there. Okay, go non-planar. I'll try to draw like this way. 1, 2, 3, 4, 5, 6, 7. Yes, negative charge is here. So these all actually become non-planar molecule. So lobes are not parallel now. These lobes are like this way. These are like this. These are like this. And this is like this. So it is not conjugated. Okay. So what will be there? It then not conjugated. One criteria is not fulfilled, right? So it will be non-aromatic. If any of the criteria are not fulfilled, it will be non-aromatic, right? It will be not planar. It is not planar, so non-aromatic. Here 1, 2, 3, 4, 5, 6, 7, 8, 8 pi, but not anti-aromatic. Anti-aromatic? No. It is again the tub shaped. I have told you previously also. In the non-aromatic portion. This is this. Okay, tub shaped, non-aromatic. It is not planar. One criteria is not fulfilled, then non-aromatic. Here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pi electrons. Here what is happening is that this system is not non-planar, it is planar. Okay, so you have to have the idea. Few examples you have to remember. Okay, because in the exams these kind of questions are actually frequently coming. and you have to have the idea, because for non-aromatic system, for this kind of non-planar structures, you have to have idea about structure. Okay, there is no trick, nothing I can tell you. Only for the easy, it will be easy to remember like that way. When heteroatom is present in this system, 7 uh, membered ring, when it is there, then when heteroatoms are present, like the normal way, anti-aromatic will be there. It will be anti-aromatic, but when negative charge is there, it will be non-aromatic. And in the case of 8 membered ring, it will be non-planar, non-aromatic. But when it comes here, negative charges are actually came, then are come, that time actually it will be planar again. And 10 pi, 4 into 2 plus 2. 4 into 2 means 8 plus 2, 10. So here n equal to 2. It will be aromatic. Aromatic. Here 1, 2, 3, 4, 5, 6, 6, 5. Positive charge, whole conjugation, and it is planar. Okay. So 4 into 1, 4 into 1 plus 2. Okay. So 6, 5. It will be aromatic again. Next. This is very important example. So count the number of pi electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pi. It is following 4n plus 2 number of pi electron rule, right? It is following. But here, for this 2 hydrogen, there is steric repulsion between 2 hydrogen. For that reason, it goes to non-planar state. Actually, you can see here, this is upside, this is downside. Okay, so in the non-planar structure, what will happen? Conjugation will be disrupted, and we know that any of the criteria are not when fulfilled, then it will be non-aromatic. Non-aromatic. Here actually hydrogen molecules are present. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 pi electrons. 12 pi electron, it should be 4 into 3, 4 in number of pi electrons. But for the steric hindrance of this kind, this hydrogen, 3 hydrogen, it will be in non-planar state. So it will be non-aromatic. Okay. Now coming to here. Here is also hydrogens are there. But when we increase the carbon chain, the number of carbon atom in the this kind of molecule, this is actually called aniline system, a monocyclic system having all the conjugated double bonds, the highest number of conjugated double bonds. So these are called actually aniline. This is 16 alanine, I think. This is 16 alanine. 16. Okay. So what is happening in the case of 16 alanine? So when the structures become actually bigger, the cyclic system is actually became bigger. Then what is happening is that the hydrogen, the distance between hydrogen becomes very little large. So that's why the steric hindrance is now less. So what is actually experimentally found out that in low temperature or normal temperature, it will act like, as it has 16 pi electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, sorry, 14. Uh, 14, 14, 14, yeah, 14 pi electrons. So it will follow 4n plus 2, 4 into 3 plus 2, right? should be aromatic, but experimentally it is found out that in low temperature it will follow this Huckel rule, and it will be planar, so that it will be aromatic. Okay, but when high temperature is given, it will be sorry, non-aromatic. Okay, so this is the thing here. So if anything is not given like low temperature, high temperature, then we will consider is like aromatic. Okay, as the ring structures, the structure of the cyclic system is bigger now, the steric hindrance will be less. Okay, now this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is 16 aluminate. Okay, 16 aniline will be anti-aromatic. 4 and 4 into 4. Okay, here this is 18 aniline. Okay, so in the case of 18 aniline, what is the thing here? Here, steric hindrance, you can see what kind of bigger structure it is. So, steric hindrance will be not here. So, only the 4 into 4 plus 2. So, here n equal to 4. So, it will be aromatic. Okay. So I have shown various complex structures also, and also simplest structures. So I have also you have practiced with me, so I think it is clear to you now a little bit, but here I know it will be confused. But don't worry, if you see the structures 1 or 2 times, you will remember this kind of structures. Only the confusions will be here. 7 and 8 members member ring. So please take your time and practice it more. The questions, if you solve the questions more, it will be clear to you. Okay. Oh, and this kind of 18, 14, 16 aniline, and here this is also very important. So many questions are there, like where these hydrogens are removed, how can we make this kind of non-aromatic system to aromatic? One possibility is here, this, like this way. If we can remove hydrogen and place a bond between these carbon atoms. Okay, then the whole system will be planar, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pi electrons. This is an alkaline molecule, right? So it will be aromatic. One other possibility is that we can put bridge atom, right here, X. This is bridge atom X. This is bridging between these two carbon. Okay, the hydrogens are gone now. So you can see here in the bridging atom what can be here. Many heteroatoms can here, like oxygen, okay, NH, and also carbon CH2 can be here. So if we can put any bridging atom here, so the whole system will become now aromatic. Okay. So these kind of questions are also you can see aromatic. So if this bridging atom, this structure is given, you think it like that way, that here also steric hindrance was there. So bridging atom also can create any steric hindrance or not. So this is the thing here I have explained to you. So in this case, it will be non-aromatic. But when we are removing these two hydrogen with a by a bond or a heteroatom, this will be aromatic. In this case also same thing. If we put a bond in here, it will become aromatic. Okay. So coming to the next part now, quasi-aromatic compounds. What are these? So many things are there, right? But it is not very difficult. Okay, so it will be. It is basic actually. You have to remember these all things. So the properties or some characteristics of this kind of compound. It is polar, cyclic. It has high dipole moment and follows Hooke's rule in charge separated form. What does it mean? So if we take this kind of example, this is the example of they are saying that quasi-aromatic compound. How can we say that? Here 2 pi electron is there, but another 2 pi is present here. Will it be, we should count it or not? We don't know, right? I am here to help you. Don't worry, okay? So, okay, let's take this charge separated form means. So this kind of bond actually, this kind of actually compounds are not very much stable. Okay, here ring is here, ring, three-membered ring. It has strain and it, only this ring is not stable much. And again we are putting sp2. It is making it putting double bond and making it sp2. So sp2 has the need of more bond angle, right? sp2 120 degree needs. But here you can see very less bond angle, like almost 60. Okay, so there is a strain. So for that reason, this kind of compound, for this kind of compound actually, it goes to, and also not only that reason, uh, one other thing is there, this bond is polar. Here oxygen is present, which has higher electronegativity than carbon. So that this kind of charge separated structures can be formed, positive and negative. Okay. Now you can see here this part, 2 pi electron and conjugated. So it will be aromatic. Okay. So this kind of compound has very high dipole moment. How? So positive negative charge separation is there, and after charge separation, it follows Hooke's rule and it will become aromatic. So it is stable form. So in stable form, it has charges, positive and negative. So that's why it has high dipole moment. Okay. So some applications of this aromaticity, we can say. So we know that this kind of molecule 4 pi electron, it is not very much stable. It is anti-aromatic. Okay. So this is not stable. Anti-aromatic compounds are not stable. Okay. So it dimerizes very quickly. It goes to like this way. Okay. It is not stable in this form. So what will happen when sodium metal is added to this system? What will happen? Sodium metal, what a metal can do? Metal can actually, metal has a lot of free electrons in it, right? So it can goes to Na plus form and give one electron, remove one electron. Okay. So if two sodium is there, two Na plus and two electron. Okay. So these two electrons are actually goes here. One here, two electron already present. If we break one, for your understanding purpose, actually I am drawing this. This is not a stable form. Free radical. If we imagine that here free radical is there, and then one electron from here is attaching with this electron, and one electron is there left here. Okay. So what will actually the resultant molecule will be negative, negative. Okay, clear? So now this anti-aromatic compound, after giving the sodium metal to it, it becomes aromatic. How? 6 pi electrons. You can see, right? Okay. So this is very interesting example. Now the next example. So here Fe 3 plus is given. It is metal, but it is in 3 plus form. You have to understand this because we know, right? Fe can show actually +2 and +3 oxidation state. So it is in its highest oxidation state. So it can now accept electron, not donate. It cannot donate electrons. So what will happen? Here electrons are there. We can imagine it like this way. If radical can be formed, here two electrons are there, right? So Fe can accept electron one by one and goes to Fe plus, okay, and sorry, to Fe 2 plus, okay, and here what will happen? Plus and plus. You are confused? Are you confused? Okay, let's. I will. Uh, I will explain you again here in a step-by-step manner so that you can understand. I'll make you understand this. Okay. So 3 plus is there, right? It will accept one electron from this free radical here. So it will become Fe2 plus. Okay. When 2 Fe is there, 2 electron it will give and 2 Fe2 plus. Here it is. And 2 electrons are actually taken by it. So here no electrons are there. So positive charge. So 2 pi electron, n equal to 0. So 4n plus 2 aromatic. Again the same thing. Non-aromatic compound. Oh, sorry, not non. Anti. Worse, right? Anti-aromatic compound has become aromatic. That's why it is important. Now, one interesting observation. So let's take this compound. When we are putting Ag or the medium, in the medium we have added silver, it is shown that the product will be this, but the question is, will it be favorable? Is it a favorable reaction or not? Okay, that is the question. So we know that for in the practical also we have actually done that for the taste of Br, actually AgBr is forming and it is precipitated also, yellow, whitish yellow kind of color. So a precipitation, actually these precipitation kind of reactions are actually very fast, but we have to remember that here another component is here. This, is it stable? If it is, this cation is stable, then only this reaction will go to forward. Okay, because here precipitation happens, it will be favorable obviously, but this cation also it should be stable. How we can see the stability of cation? Here again comes the aromaticity. You can see the aromaticity has diverse application. In any this kind of stability of cation, or to know about the acidity, various questions are there, acidity and also dipole moment. In many way, actually aromaticity can help you. It can explain where nothing can explain you, aromaticity it will come. So you have to have the basic idea and clear cut idea about this chapter. See how important this is. This reaction is favorable or not, we can say from aromaticity only. Okay. So let's check the stability of this cation. 1 2 3 4 5 6 6 pi electrons, conjugated 6 pi electrons, planar. We have seen na, negative charge if they are, then it will be non-planar, otherwise it is planar. So it is Aromatic. Aromatic, it is stable, so the reaction is favorable. Yes. Here, the same thing. Same thing. Ag is given, AgBr is precipitating, but is it a favorable reaction? Okay. Here we find the answer, right? We found out the answer. Here, favorable. Yes. Here, question mark. Is it favorable? Let's take again the carbocation stability. Aromaticity, we know, right? So just check when we are finding any cyclic, conjugated or not conjugated. Cyclic structures are there with pi electrons. We can apply the Foucault law and this all the concept of all the chapters. Okay, so 4 pi electron, conjugated cyclic 4 pi electron. It will be anti-aromatic, anti, which is least stable, least worst condition. So it will not favorable. The reaction is not favorable. Okay, the answer is here. You can see this kind of questions actually comes in exam. Now another question. Answer it quickly. The rate of solvolysis of the following compound is. Now solvolysis. You are confused again, right? Okay. Let's come to the now first solve what is solvolysis. Okay. Solvolysis is a reaction. Solvolysis is a reaction where solvent molecule, okay, for a reaction we have to give a medium, right? The solvent molecules are there which are acting as a nucleophile. Sorry, only any Y nucleophile. Okay, so solvent molecule is acting like nucleophile and the reaction is going through SN1 pathway. This is called solvolysis reaction. This is a kind of substitution reaction where the solvent molecule is acting, no other external nucleophile is added, only the solvent molecule in the reaction medium is acting like a nucleophile. Like water, sometimes we are seeing, you have seen water molecule can through oxygen it can attack. So that kind of reaction is called solvolysis reaction. And in solvolysis reaction, the reaction goes generally it goes via SN1 reaction. So I have to tell you because I have not teach you SN1 reaction. So in the SN1 substitution nucleophilic 1 means order will be we will be 1 means in the rate equation only one concentration matters. Okay, so the mechanism in the mechanism only you just remember that in SN1 reaction carbocation forms as a intermediate. Carbocation forms in SN1 reaction. Okay, so first the carbocation will form and next in the next step what will happen, let's say H2O molecule will act. Okay, that is the thing. So in these cases what will happen, the rate of solvolysis. So here in SN1 reaction the rate only depends on the concentration of carbocation, means in among the following four reactions the reaction in which the carbocation formation is faster or more amount of carbocation is forming, so then the reaction rate will be faster. Okay, so if you are confused, I am again telling you in a short way that solvolysis is given. We know solvolysis solvents are attacked actually, and it goes via SN1 reaction where actually carbocations are formed. So depending on the carbocation stability, we can tell the reaction will be faster or not. Okay. So rate of solvolysis, rate of SN1 rate proportional to carbocation stability. When carbocation is stable enough, then the reaction will be faster. Okay. So when carbocation stability is more, the reaction will be faster. Okay. That you understood. Now see, in the given four compounds, if they form carbocation, which will be stable and which will be not. Okay. So if it is for going to solvolysis, it will give this carbocation, right? From here, this carbocation, here, this carbocation is there, and here only Br we have to remove, because in SN1 reaction, first the removal of the leaving group is there and form the carbocation. Okay. So we have nothing to do with solvolysis and SN1 here. We have to again consider the aromaticity to check the stability of these four cations. Okay. First we have to see which is aromatic. We have to count pi electrons. Okay. So here 2 pi electron. Here 4 pi electron. Here 2 pi electron again. Here 2 pi. Okay. So one is 4 pi, others are 2 pi. So 4 pi anti-aromatic, least stable. So we will not consider this. Now we will see these three. Okay. This we know this is aromatic, obviously. This is not. If you see, this has conjugation, but not fully conjugated. So it has a conjugation. It has some extra stability, but not much. Here, is it conjugated? No, it is not conjugated. So because in bridgehead position, if the conjugation is happen, then double bond will go to this way, right? But it is not. This is forbidden, because these positions actually called the bridgehead position. So bridges in the bridgehead position, actually carbocations are not stable, and also for the ring angle strain, and also the conjugation is not possible because double bond here will be not stable. So this will be not stable. So what will be the order then? This is aromatic. This has conjugation, but it is non-aromatic. Okay. And this has no conjugation also. Okay. And this is anti-aromatic, least stable. So we know that stability of aromatic will be more than non-aromatic than anti-aromatic. Okay. This we know. But okay. So now this is 1, 2, 3, 4. So 3 has highest rate because it is forming aromatic carbocation. 3 has highest rate. After that, it has some conjugation, right? So 2 will be there. Then this doesn't has any conjugation, but still it will be more stable than anti-aromatic, because anti-aromatic compounds are experimentally it is also proved that these are less stable, least stable. So 1 and then 4. Okay, this will be the answer. Please match it with your answer. Okay, now among the following compounds, the one which has highest dipole moment is dipole moment. We have previously seen dipole moment for the quasi-aromatic compound, but in that case there was actually oxygen molecule. What we will do now? Okay, so we have to consider this double bond. So we have to calculate, right? So we have to consider that if we break this double bond in some manner, so that we can gain some extra stability or not. That's how actually dipole moment means. We have to see the charge separated form, right? So let's try that. For this case, if it goes like this will be okay. It will be positive, it will be negative. Other double bonds are there. So it will become 1, 2, 3, 4, 5, 6, 6 pi, 4 pi. It is aromatic, but it is anti-aromatic. So it is a whole compound, right? So one part is aromatic and another part is anti-aromatic. It will be unstable, not favorable. Only it will be favorable when after charge separation, the whole system will be aromatic. The two parts are aromatic. That in that time only that system will be stable. Here one part is aromatic, one part is anti-aromatic. So this will be not stable. Okay. So we have to find the highest dipole moment. So we have to find the structures where charge separated forms are stable. When it will be stable? When it will give you two aromatic parts, aromatic moieties. Okay, we have to find out that only. Understood? Then try it yourself. Okay. So if there are two possibilities, okay, we have to check two possibilities. If we break like this, then it has then positive charge and it will then have negative charge. Okay, 1, 2, 3, 4, 5, 6. Okay, I can remove that. So now 1, 2, 3, 4, it has negative charge, right? 1, 2, 3, 4, 5, 6, 6 pi. 1, 2, 3, 4, 5, 6, 6 pi whole conjugated system. So it is aromatic, it is also aromatic. The whole system is aromatic. Okay. So we don't have to see the other option, like if we break it like this way. Okay. Because we have found it in this way only, it is aromatic. Okay. Next, see, if I break it like this way, this will be positive, this will be negative. This negative will be non-aromatic. It will be aromatic, but as the both the parts are not aromatic, the system will not be stable. Here the part is okay. If we break like this way, negative, positive, it is stable, but not the this system is aromatic, but this part actually is not aromatic, right? So it has less stability than this. So we have to find the highest dipole moment. Okay. Oh, this other option also we have to try, right? I'll solve it in a. I am trying to solve it in a clear way that you should remember. That's I am thinking that if I make a clear description or explanation to you, then you can never forget it. Okay. What I did previously, this way I have it, right? If I break the bond like this way, it will be negative, negative 4 pi, anti-aromatic. It is not stable. Okay. So only this option has all the aromatic systems in charge separated form. So it has the highest dipole moment. Answer will be B. Next, Same type of question is there, but see what the question is asking. Among the following compounds, which one has lowest energy barrier for cis trans isomerization? We know that in double bonds, cis trans isomerization is there, where A, B, this is trans, and it can go, if it can go to this way, B, it can become cis. But in double bonds cannot rotate. So if rotation is forbidden, it cannot go to this way, right? If rotation is forbidden here, rotation is not possible, then how can B will be like this way, right? How can B can go to upside? It will not, right? So see what the questions are asking. Among the following compounds, which has lowest energy barrier? So there is energy barrier, right? Rotation is needed for the cis trans isomerism, transform to cis form. This kind of changing or isomerization only possible if the single bond, if the compound can be stable in the single bond kind of structure, what to say. So if there is no double bond, like if we break the double bond positive and negative way, it will become now a single bond, then it can rotate. But when the energy barrier or the this kind of charge separated form will be stable only if the, like the same way, only if the in the charge separated form two parts will be aromatic or stabilized, then only charge separated form will be stable and it will then rotate. So it has a lowest energy barrier for the crossing, for the formation of cis to trans and trans to cis, right? Like that way. If it has positive and negative, if we can break this trans form, this single bond is there now, it can rotate. Now it can rotate and goes to upside, goes to cis form. Okay, this is the idea. So again we have to find out that in which form, if we break this double bond as positive and negative, in which form it will be stabilized. Let's check. If we break like this, sorry, if we break like this, then positive charge will be there and negative charge will be there. But in this system, no pi electrons are other than negative is there, so no conjugation. These are sp3 carbons. So this system we will not consider, right? Here, if we break like this way, both are five membered ring. So any breaking, the two breaking ways will be same. Okay. So negative, positive, 4 pi anti-aromatic. Let's not talk about this. Now, like this way, negative, positive, 6 pi, 6 pi. Overall aromatic. This will be answer. Because now this kind of charge separated form, because now in this kind of charge separated forms are actually stable. Sorry. Now this kind of charge separated forms are stable, right? Negative and positive. Here, negative and positive. Okay. So this will be whole system as it is aromatic. So this kind of charge separated form will be stable, and so that it has a single bond, then it can rotate and it can goes to cis and trans, right? So this will be the C will be the answer. Among the following compounds, which one is anti-aromatic? Okay, it is simple, right? There is no tricks here. So which one will be anti-aromatic? Here one is sp3 group is present. It will not be anti-aromatic, right? It will be non-aromatic. Sorry, it will be homoaromatic. Other part is aromatic, right? Homo. Here positive charge is there, 4 pi. We have found that, right? Here it is not planar, so the whole conjugation is actually not here, so it will be non-aromatic. It is not fully conjugated system. It is quasi-aromatic. We have to find out the anti-aromatic. 4 pi, obviously it is anti-aromatic. I was actually trying to explain all the options. That's why I was actually a bit late. But yes, you will understand that we have found out the answer, right? B will be the answer. So these all questions are from CSIR NET previous year questions. So I have taken a few questions and also practice. I have for the practice purpose, I have also incorporated various structures. You have seen this. Now coming to one new part, some questions are also asked from this, so that's why I have incorporated this part also in a simple way. You will understand it. So Craig's rule, what it is saying. So let's not talk about this, what it is saying or how it is coming. Nothing. This is important, but not much. Okay. So we will just understand the conditions and the rule, only the rule, how we are applying the rule. Okay. First condition, non-benzenoid polycyclic compound. It should be non-benzenoid. Benzene ring should not be there. Polycyclic, more than one cycle should be present in that compound. Second one, C2 symmetry must be present. Means C2 molecules must possess one symmetry through which it can be rotated. Okay, rotate and so that it can come to the same position again. Okay, if these two conditions are fulfilled, then only we are coming to the rule. We first check these two conditions. If fulfilled, then we come into the rule. If the number of pi bond is n, then if n is odd, it will be aromatic. If n is even, it will be non-aromatic. Okay, no anti-aromatic here is here. Okay, so in Craig's rule, compounds can be aromatic or non-aromatic. These are the two conditions. We have to see first two conditions. If the two conditions are followed, then only we have to count the pi bonds. According to the pi bonds, if it is odd, it will be aromatic. If it is even, it will be non-aromatic. Simple. Let's take an example. This benzene rings are not there. These two are 7-membered ring. So non-benzenoid. Polycyclic, obviously two cycles are there. Cyclic forms. Cyclic parts are there. Okay. First one fulfilled. Second, C2 symmetry must be present. Where? From where? Let's see. This. C2 means when we when we rotate this molecule in 180° through this axis, you will find the same molecule again. If we rotate through this, you can imagine, if we rotate through this, we will find the same. Okay, let's take this again like the previous lecture. See, if C2 present here C2 is present, right? If we rotate 180, it will be the same again. So C2 axis here present because the both halves are same, you can see. Okay, so second condition is also fulfilled. Now let's count the pi bonds. We are coming to this part. 1, 2, 3, 4, 5, 6. 6, n equal to 6. So even it will be non-aromatic. Simple. So here it is complicated from Huckel's rule because it is for non-benzenoid polycyclic compounds. we have so far we have not talked about this, but in the questions when our various structures are given to you and the question is asked like which are aromatic, non-aromatic, like this way. So you have to just keep this in your mind that if you see non-benzenoid and polycyclic compound, only Huckel rule will be not considered there. Okay, you have to consider the Craig's rule. Please keep it in your mind. So when various options are given, so it will be very much helpful. That's why I am teaching this to you. So another example here. Okay, non-benzenoid obviously, polycyclic obviously, C2, C2. Where is the C2? This not. This can be the C2, right? Put this and this. Yes. See, everything is same. So if you rotate through this axis 180 degree, it will you will again got you will again get the same one. Okay. So two conditions are fulfilled. Now count down the pi bonds. 1, 2, 3, 4, 5. 5 n equal to 5. Odd, it will be aromatic. Okay, it is non-aromatic, it is aromatic. So so till now I have given you the simple idea about aromaticity, what is aromatic compound, non-aromatic, anti-aromatic, homoaromatic, and quasi-aromatic. All I have tried to explain you in a simplest manner, and also you have practiced a lot with me. So hope you understood all the things here. And most important thing is the question solving. So you have to practice a lot to because it is easy, the chapter is easy, but question the mistake can also arise in this chapter frequently. So you have to practice a lot, and don't forget the Craig's rule also, that is actually coming from that also actually questions are coming, so that's why I have incorporated this also. Hope you enjoyed this session, and please feel free to comment down if anything is complicated to you. You found it complicated or simplification is needed. I am happy to help you for that, and the session will be go on. This is only the chapter 2 or topic 2. So let's learn together. Okay. Thank you so much for listening.